In this video, we're going to discuss the normal distribution. We're going to talk about what it looks like, what it's used for a little bit, some of its characteristics. We'll talk about transformations. We'll talk about whether testing for normality using the QQ plot. And we'll also bring up one very important thing in vision science, which is this converting from Snellen acuity to a logMAR in order to achieve normality in our distributions and do parametric statistics. So let's start by taking a quick look at the formula for the normal distribution. Where did it go here? So that's right here. Let's see if we can make that a little bigger. And basically, we talk about parametric statistics. And the word parametric means we have parameters. And in this case, in the case of the normal distribution, there are really two relevant parameters. There is, this is interesting. In this formula, they kind of erase the parameters. The z-score, z, if you remember, is replace this z with x minus mean of x, that quantity, x minus mean of x, divided by the standard deviation. So the two parameters in a normal distribution are the mean and the variance. It's squared, so it would be you would get out of this the mean squared and the standard deviation squared, which is the variance. So we talk about parametric statistics when we talk about the t-test, analysis of variance, chi-square, all sorts of statistical tests are called parametric because they have an underlying distribution, and that distribution has parameters. In the case of the normal distribution, it's the mean and standard deviation. Now, the normal distribution has some characteristics that are very useful to statistical analysis. And one of them is that it just, as it's, the main one is that the distribution of means, sample means, from a theoretical distribution of sample means. So when you do a study, you calculate the mean. Well, consider if you had done that study an infinite number of times. The distribution of the means from that study would form a normal distribution, no matter what the original shape of the underlying observational data would be. The observations could all pile up on the left here and, just get this big skew. But if you sampled enough, if you did maybe a big skew like that, you do a couple hundred observations, take the mean, and then you imagine hypothetically that you do that an infinite number of times, the distribution will form this bell-shaped normal distribution, and in which 68% of the observations, those sample of means, is called a sampling distribution in the terms of the samples of means. The sampling distribution, 68% of the means would fall within plus or minus 1 standard error. Standard deviation in a sampling distribution is called a standard error. So it's still the standard deviation, we just call it a standard error because this is a special hypothetical distribution of means. 95% of the distribution of the observations, the means, sample means, it's hypothetical sample means, 95% of them fall within plus or minus 2, and 99.7 fall within plus or minus 3. Here's our z-score. x minus mu over sigma. All right. Now, sometimes things don't look normal and the data is right skewed. And you want to use parametric statistics, and one of the assumptions of parametric statistics is the underlying distribution is normal. So you want to fix those variables so that you can use this distribution. And so you log transform them. And a good example of this is converting from visual acuity to logMAR. We do this because there's just a lot of mistakes in people taking the average visual acuity. So let's see an example. Let's go to our t-test simulation spreadsheet, and we're going to use this to do some data. First, let's look at this paper. This was an editorial. I forget what the journal was, but basically, if you have the, now decimal acuity means like 2020, that decimal is 20 divided by 20 is 1, 2040 is 0.5. You take the minus log of that 2040, 20 divided by 40, and you that gives you the logMAR. Same way, if you have the logMAR, then you take the negative value of that logMAR and you raise it to you exponentiate to 10. So it's the anti-log, 10 to the minus logMAR. All right. So in this example, I have generated a random list of a random set of numbers that have a mean of 0 and a standard deviation of 1. That's just like on this figure right here. There's the mean of this normal distribution is 0, and it has a standard deviation of 1. Standard deviation in a sampling means is also called the sampling distribution, or we're calling them standard errors. But we think of them, it's just the standard deviation is, or the standard error is just the standard deviation of the sampling distribution. So we've generated this random set of numbers. And let's come over to our little graph here, kind of change it around a little bit. Let's go. This is what our, oops, well, it's been abbreviated. Let's see. Come down here. Point of all this is just to show you we have, this is the random distribution of those z-scores. Remember, we get that by taking a frequency, and here we have the data that goes down 1,000 samples, and the frequency is calculated here, and then the numbers beside it. So you can see it's bell-shaped. And then we convert to logMAR. Now let's just kind of step back a minute, and let's note that, for example, the mean of our distribution, we want to convert from a z of 0, with a standard deviation, to 1. We want to make this a, let's see, what did we do here? Oh, that's funny. Okay, so we have, we're going to convert from a mean of 0 and a standard deviation of 1 to a logMAR value with a mean of 0.301 and a standard deviation of 0.5. So let's see how we do this. First of all, how we convert. So we got 2040. 20 divided by 40 is 0.5. So our logMAR is minus the log 10 of 0.5. So logMAR equals minus the log of the decimal acuity. And then just to kind of show how we can get back to that, we can take the log of, let's see, we got this. Now we want to go the other way. So we can go 10 to the minus A4. And that gives us 0.5, which was back where we were. And then we can take 20 divided by A4 to give us the denominator of 40. All right. So that's what we did on all of these. We went through and we first converted. Now, to convert to any scale you want to from a z-score, basically what we do is we take the mean, that's A2, that's 0.301. We add the standard deviation times the value x. So this value is 0.30100 plus 0.5 times 0.21472, and we get 0.40. And then we just go down and we do that for everybody of the 1,000 random samples. Then we want to convert to VA, back to our original, or we want to find the visual acuity number of that. So remember we took 10 raised to minus the logMAR, and then that value divided by 20 gives us the denominator of the 2040. So this would be 2051. This is 2022. And so we do that for all 1,000. Now let's take a look at our distribution of the logMAR. That's our z. This is our z. So let's redo our little graph over. Oh, that's, yeah, z. And I do the logMAR. And here we get another, a nice bell-shaped curve of the logMAR, which kind of mirrors, it's a little thinner, but kind of mirrors the chart of the random numbers. Now then, I have actually down here done the acuity. And so these values look at our frequency. And our frequency are the VAs that we converted, the range going from 0. Notice on here I go to 260. When I do this formula, let's come out of here. Whoops, cancel. Let's highlight. What I'm going to do is I'm going to highlight not just to the 260, but I'm going to add some, because there are values. This is so skewed. There are a number of values that are even beyond this high value. So I add an extra blank down here, so everything above 260 will fall into this extra little bin here. Then I highlight this, and if you remember, in our frequency, we go equals frequency. We highlight the data, the data array we want to collect, and the bins. And then while we've highlighted this, and then we highlight this whole thing here, but we're in the first cell. This formula is only in the first cell. We go Control Shift Enter, and it calculates all those. It comes down here and it says, okay, we have 1000 minus 54 values that go from 0 to 260. And again, and then you can see these 54 pile up at the end here. So I'm not quite sure why that goofy thing stopped and made that graph look like that, but it's okay. So you can see that if you use visual acuity, you got this highly skewed distribution. Now let's take a look at this right here is our average of our logMAR values. And it's 0.29678. And if we take that value, 10 to the minus that value is 0.5, which is where we started from. We said we were at 2040, and to get the denominator, we divide 0.5, or this value, 20 divided by the 0.5 gives us 39.6, and that's pretty close to our target of 2040. And so we started with 2040. We did a random sample. You know, you're not going to get exactly 0.5, but we came pretty close. And if you round it, you get something that looks like that. We could give that a few more. I guess it works out. So that's what we got for logMAR. However, notice that when we average the acuities that we got, so for each of these logMARs we convert back, we get this array, and the denominator is 75. So if we used the Snellen acuities in our study and we averaged them, we would say the average acuity was 2075. When in fact, if you convert it, do the transform, you get a much more reasonable number of 2040, which is what we were starting with, and what the true underlying mean is 2040. Converting it to this value here, because of the skewed nature, this tail really makes the mean much bigger than it really is. It distorts it. So that's why we do a log transform. All right, well, let's say we have a set of data and we want to test. Is it normal or is it kind of skewed or something? Well, when we do that with a QQ plot. And so, for example, here is data. This is a set of EEG values. And we have a whole bunch of them. There's 5. We have 5 EEG waves: delta, theta, alpha, beta, and gamma. And we have them in 4 locations: 2 temporal and 2 frontal. And so for each one we have 4. Now we're going to let's do a analyze frequencies and do a histogram on a combination of theta, beta, theta beta, and log theta beta. We're going to do our charts, histograms, and we see here is alpha theta. You know, it's not exactly bell-shaped, but not too bad. Oh, and there were 3 tasks. There were different tasks that these brainwaves were accumulated. This was an EEG task. We have one that's a memory task. This was just, the person was just sitting there getting their waves measured. Let's look at beta. Again, it's not exactly a perfect normal distribution, but it's kind of bell-shaped. If we look at the ratio of theta beta, so the ratio of 2 normal distributions is usually not normal. And you can see here it's skewed. So when you have a ratio, you don't treat it as a normal distribution. What you can do, though, is take the log of it again. And now this is the log of theta beta and much closer. Go to a different task. Here's theta again, and this is the learning task, a word pair learning task. Theta's kind of normal. Beta's sort of normal. Theta beta is real skewed. The log of the theta beta is normal again. Here we have a memory task. Sort of normal. Sort of normal for beta. Theta beta is highly skewed. Log theta beta getting kind of normal again. So those are the histograms. Now, we can also look at our QQ plots, because these, when we were saying sort of normal, we get a better idea from this. So here are the same things, and we're going to do QQ plots. And it's thinking, it's done. Let's go. This is our task. This is theta. Now, the idea of the QQ plot is we have our expected normal distribution over here based on the frequencies that we got. So we look at the cumulative frequencies as we go across that histogram. We calculate, find out the z-score for that, the probability distribution underlying it, and then we plot it out here. Plot out the z-scores. We do the percentage, the probabilities, the percentages, sum up the proportions, find the corresponding z-score on the normal distribution. For example, if we were going from 0 to 1 here, we would, at this point, half the distribution has been, so if our value was right here, half the distribution was to the left of that point. So we'd add them all up, and we would find the z-score at 50% is 0. At 68%, well, 68 plus the tail here, actually that's 1 minus 68, so what is that, 22, 32, 32%. So 32, we would have 38% over here, but our z-score would be this value right here. And so we get our z values and we put them into the graph on the left. And then the raw proportions from the observed value is on the x-axis, and the line should be straight if it fits a normal curve. And we can see for theta, not too bad. We come down here to the next one. We have theta, let's see. Oh, so this was theta for the EEG. This is beta. Again, we can see it's pretty straight. Theta beta, oh, look at this baby. It's got this big bend in it. We don't like that. That's demonstrating the skewness. And we come back to the log. You know what? It wasn't perfect, but it came much closer to a normal distribution by logging the values that went here. Okay, so that's a QQ plot. And that is about it for our discussion. Yeah. All right.